Welcome to Morpheus Chair, the program where you learn to build robots like these. So, in this video, what you're going to learn with me is the first steps to use Dynamixel servos, which are these servos that are used in this robot arm, to build really whatever you want. And what you're going to learn is how to use the library from Robotics to move it through position with a Python script, basically. And this is the first step to then get a bit closer to the move it, which is a totally bigger and heavier monster that we have to battle. But step by step. So today we're going to move it through a Python script, the joints, and you'll see that it's quite easy. One warning: any robot that you build, you have to be careful, especially in these kind of robots, because these servos are powerful. So be careful when the robot moves, because you can get your fingers or your face in the trajectory of the arm, so be careful.
Be safe.
And without further ado, to the workbench. So let's start, like always, remembering that all the code that we generate here will be found in these two Gits, where we put the notebooks with the instructions, and then all the code that we do for this video tutorials will be inside this Git, okay? Each episode, I'll upload everything that you'll need in that episode. So first things first, I've launched ROS Development Studio ROSject just because we have the notebooks and because we are going to use it to see the code and also to connect to the real robot remotely and execute everything remotely. But you can do everything that I'm going to do here in ROS Development Studio. You can do it locally as you wish. It's just that using ROS Development Studio, you'll be able to do it remotely also. And when we progress in the episodes, in the ROSjects, you'll have more and more code ready to go. So let's go to the episode 2, control notebook. So first of all, a warning: we are going to work with a robot that moves and can cause injuries if you're not careful with it. So be warned and be careful when you're working with robot arms, especially because normally they don't have force feedback. So if you get a finger stuck there or something, it can be really, really harmful. Okay? So be careful with this. How to get started? So the first thing is, okay, we're going to connect our robot. So you've built the robots, the robot arm, or your own robot arm based on the open manipulator schematics, as you wish. But now we have to know how it's connected to our Ubuntu system. So let me go open a terminal in the system that has connected the USB. Okay, so if we go here and we execute this command, let me write reset and then this, you see that if I disconnect the USB, it says device TTY USB 0 has been disconnected, and when I connect it again, it says exactly attached to TTY USB 0. This is really important because it's the device name used in Ubuntu, in Linux. So this is used for us. We are going to use it to connect to the real robot. So you can also get more information about the element that it's connected with this command, ls usb, which in this case we have this Future Technology International single blah blah blah. If I disconnect it, it's not there. Okay, so we know that that device is the device that we are connecting. I leave in the video description all the hardware that you need to make this work, but here we're supposing that you've built the robot arm using the Dynamixel motors, okay? So let's launch the position control. We'll go into detail on how it works, but so we're going to go to our Open Manipulator workspace, where you've downloaded all the code that we have here in the ROS jet. You see that we have this code, so this code will have to be downloaded in your Open Manipulator workspace in the device that you are going to connect the robot to. It can be a PC, it can be a Raspberry Pi, anything. So we're going to launch this Dynamixel Workbench controllers. These are packages created by Robotics. So we go here and Dynamixel, I think it's controllers, Workbench controllers. And we have the source, there you go, and the launch, which is position control. There you go. So this is the code the same code that we are going to execute here. Yeah. So let's see it here just to be sure that it's the same. So we're going to go here, and it's inside this Dynamixel workbench controllers. There you go. And position control. So as you can see here, we are using as device name the TTI USB. Depending on your system, you'll have to get the one that it's published through the commands that I just showed you here. This one, okay? So you'll have to see which device is given, which device name is given, and change it here. Also, one of the things that normally happens is that the baud rate is not correctly set up. So if you launch this and it's not correctly set up, you'll get some message like this, which is baud rate, blah, 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 whatever, whatever. Okay. One of the ways we can do it is using the device name that we know already. We go here. Oh, sorry. Yeah, I have to connect it first. There you go. So now, there you go. So it says that my speed is 3 million baud. Well, 3 million, okay? So that's the one I have to put. Yeah, so I have to put that here, which is perfect. And that's quite it. You can leave the other elements by default. We're not going to touch it or talk about them. And essentially now we can launch the control. So if we go here, and very important, we source always. So and ROS back profile. And then we launch the control. There you go. So now the robot should be stiff. So you shouldn't be able to move it. Yeah, all the servos should be stiff and in their original positions, in the positions that they were at start. Okay, fantastic. So now we have the control running. So we have executed this position control, and let's see which ROS topics and services are published. Okay, so if you were in your local system, you should do source devel setup.bash and ROSpack profile, ROS topic list, and you should see these topics, and ROS service list, you should see these services. Yeah. What we're going to do is connect remotely so that we can execute everything from now on through ROS.ds. For that, I've set up, let me just, there you go. So there's a web where we explain in detail how to do this, but I'm going to just show you, but you can read it here if you have any doubts. Let's go up again, around here. Okay. So the first step is click Real Robot, connect to Robot. Perfect. And now we have to put our IP. Oh, sorry, I had it here already. There you go. So you should have something like this. Okay. So you have to follow the instructions to install this inside your system, which is explained. It's basically explained here, but essentially is just executing, cloning this and executing this. That's it. And then you have to reboot your computer and you will have that for all eternity working, demonized. So you won't have to launch it or anything. Okay, so we have this, so we turn it on. We copy and paste this. And the URL. And we connect. Perfect. So now in theory, I have to put Ardani laptop as my ROS core, my ROS master. And then let me just kill this and launch it again. Okay. And then if we open a shell, we should be able to see the same exact thing that we could see locally. So ROS topic list. There you go. And ROS service list. Perfect. So let's talk about these messages. So the first thing is that we have basically three topics: Dynamixel state, go Dynamixel position, and joint states. And this will be always. So any robot that you build that uses this this control launch, Dynamixel workbench controllers position control, will do exactly the same, just that it will have different joints. Okay, so if you put more joints, then you'll have more joints. So let's have a look. ROS topic info, Dynamixel state. Okay, we see that it's that package, Dynamixel state list, as type of the message. Let's do ROS topic echo this and N1. Okay, so this is one of the publications of this topic. And what we see is that it gives us the model name of each of the joints, the servo, the type of Dynamixel that we have there. So you see that joint 1, which is the lower base, has this model while number 2 and number 3 are a different model, a more powerful one. That makes sense because they are the joints that have to do more force to move the entire robot. And then we have the others, which are the same model as the first. I've left here some documentation. So here in Robotics, I've left the link to the description, the data sheet of the servos that we're using, just in case you want to build the exact same setup. So here you are. But you can see that we have information of each of the servos, the identifiers, some stuff, and very important, the present position, and the go position also, and the go velocity. But essentially, this is the most important one, the position. You can see that it's not radians, it's raw. So essentially, if you go here, you can see that it's the absolute encoder data. And essentially 360 degrees is around 4,000. We are going to call it clicks, okay? 4,000 more or less. Okay, so we have information this published all the time. So if we go like that, it's continuously publishing all the time with a hertz, with a frequency of around 8-9 hertz. Yeah, very well. ROS topic list. Let's see the other ones. So ROS topic echo, ROS topic info of joint states first, and ROS topic echo joint states. Okay, we can see that it's the name of the IDs and the position. So essentially it's the same information as the previous topic, but in a ROS way. So we have it in radians, they are using a ROS standard message type, which is the joint state type. You can see here, joint states. And this is what we use in ROS, in RViz, and Move It. In the future videos, we are going to use it to know exactly where the robot is. Yeah? Great. And finally, we have this last ROS topic info. Whoops. Goal Dynamixel position. And you can see that there's no publishers. That's because it's a subscriber. So essentially what we are doing is we have a node that it's the subscriber, which is position control, that it's listening to this topic. And when we publish something here, we're going to move the robot. So if you have any Dynamixel connected with this setup, you can do this exactly the same way. So let's have a look. Okay, so now we're going to move it, publishing through this topic. So let's go. ROS topic, publish, goal Dynamixel position, and depending on your robot, you'll have many things to put here. But essentially we see, okay, what do I have to put here? Okay. Let's have a look at the joint states. Minus N1. And essentially we have to put the same thing. So let's go. ROS topic, Dynamixel position. There you go. Now we're going to put the velocity, which actually we're not using, but just for the sake of the argument, we put this here. Let's put a position, and let me change it, because otherwise this is the current position. So let's put here 0. Let's put 1.57 for example. Yeah, more or less. And the names, well, we have to put the names, the IDs, and that's it, I think. Yeah, let's try. There you go. So it moved 90 degrees to that side. Let's change and go and move it some, for example, minus 0.7, which is in the other direction, and 0.7, and also this joint we're going to put it like 3, I don't know. There you go. Now let's publish again. For example, this one. Great. Okay, great. So now we've seen how we can use this. We can also use this. There's a service, ROS service list. And with this service call, join command, and then we have to put the units, which would be raw if we want to put the clicks, and rad if we want to put radians in this case. And the ID, for example, should be, for example, 1 if we want to move the base, for example, and the goal position, which, I don't know, let's put 0.7. We're going to publish this. So let's go. There you go. So as you can see here, we wait for it to finish. So, and we only can move one at a time. But the good thing is that we waited to finish, and it's a service, so really easy to use. We have moved the robot with the service and with the topic publisher. Now let's have a look at the code to have a better idea of what we're doing. So we go here. This is the position control that we've launched in the device that it's connected to the robot. It could be a Raspberry Pi, and in our case here, it's a PC, a normal PC. Yeah. Okay. So here, what we're doing is giving it the device where we have to connect, the boards, and some other stuff, which now it's not important. This is important. Position control, which is the binary compiled version of this, which this is made by Robotics. And essentially is we initialize a class and we start this method, this function or action, whatever. So in this position control, we get the values that we're getting. We start the Dynamixel workbench class, which is the API that Robotics gives us to communicate and get data from Dynamixel Servos. So really important. But here is the ROS part, which is we initialize the publishers, the subscribers, and the server. So publishers, what are we looking? Well, we are initializing 2 publishers, the Dynamixel states that we saw, the first one, and the joint states, which is a version, the ROS version of this. Yeah. Then we have the init subscriber, which is this, which is the one that listens to these commands that we've been sending to move it. And finally, the init server, which is this join command, which is the server that we just used here to move the robot. Okay? So how does this work? Well, let's have a look at the subscriber here, which is this one. What we see is that we are sending the positions to this DXLW, which is this object that we talked about here at the beginning. There you go. It's the Dynamixel Workbench class. Whoops. Okay. So let's have a look again. It's subscriber. And what we are doing is getting these positions that we are getting and converting them radian to values. So we are converting the radians to these tick values, these click values, and then we are writing. That's it. There's nothing very complicated here. And in the server, we're doing more or less the same thing. Oh, sorry. Yeah. There you go. So we have a request and a response, and when we get the request, we see if we say radians, it's the one that we stated here, and then if it's radians, we have to convert it from radians to the clicks, and then we write again. That's it. So with this, you can control any Dynamixel servos by position. Great, huh? Okay, so now let's put into all that we've learned into use. So let me show you, this is more or less what we've been talking about. And now what we're going to do is create our own package that has a script inside that uses these topics and the services to move the arm. So let's have a look. You have the instructions to create it here, but I've already done it for you here. So let's close this and Morpheus chair, scripts, open manipulator. And here we have. Let's have a look. We initialize a node and then we start this. There we go. And we have, I've basically done two functions. One that tests a sequence of joints and the other one that you can move it through a GUI, the joints. So let's have a look how this works. So the sequence, it creates this class that we're going to see in a minute. Then we have these positions of all the joints. Then we generate these arrays of arrays, essentially, with append. We append each of the arrays. And once we have it, then we execute these two sequences. With a 0.5 and a 0.9 respectively of intervals between one position execution and the other, and the next one. It's a very crude way of executing a sequence of movements, but it's the most effective here. So let's have a look at this class, which you can imagine what we've done. So in this class, we are initializing a subscriber to joint states. We are initializing a publisher to the goal Dynamixel position. And then we are starting a service proxy to this joint command. That way we can use this system of moving all the joints at the same time, or we can move it one by one securely with the service. and we are subscribing to joint states to get all the information like the names of the joints, the current state, and in the future we can validate that we've arrived to that position and then execute the next one. So let's have a look how this works. It's very simple actually. So we have the joint states callback, which is getting the message here. And we do this check joint states just to be sure that this topic is being subscribed, it's working. So we have the data. So here we go here, and we have that. So we check that here, ROS by wait for service with the joint states topic name, and we wait for it for 5 seconds, I believe. Yeah, 5 seconds. And then if it didn't work, then we try again and we try again until it works. That way we have this value that's here also ready to go, because we use this afterwards for other stuff. Yeah. So when we have this, when we go here and we execute this move all joints, which is the method that executes the movement of all the joints, we give it an array and we check that one, the number of joints that we are getting are the correct number, because otherwise we can't move all the robot. And the second is that the gripper is in a safe position, because the gripper in this particular design has some issues in the fact that if we exceed these values, we could have problems of jamming systems and so on. And that's why I've placed this method here, just in order to never break the gripper, okay? This is a very good way to go, because sometimes you forget, and it's not cheap to replace a part of a robot. Okay, once we've checked that, then we just generate a joint state object. We fill it with all the joint states information, like the frame ID, the names, the velocity, and the effort, which are 0 because we don't use it. And the only one that we fill really is the position array. And when it's done, then we publish. That's it. Very easy. And the same happens with the service. So the service proxy, we use it here in the move one joint, which essentially we generate a joint request. We check that the gripper, if it's the gripper, so if the joint ID is 7, which is the last one, which is the gripper, we check that it's safe. You could do this with, for example, if you build a hexapod, then you should check some configurations just in case someone asks the robot to do something that it shouldn't. And when it's done, then we send the request. And that's quite it, really. Yeah, and if it's not the gripper, then we don't check if it's safe or not. That's it. So let's see it in action, shall we? Okay, so let's execute this marvelous script. To execute it, you just have to do 2 things. One, you have to be sure that the control is connected. So if we go here and there you go, a bit better, yeah. So you can see that it's totally rigid. So now we execute this script in your local computer or in ROS.ds as you wish. So we go to simulations, source devel setup.bash, ROS back profile. and we execute it. Let's move it a bit here. There you go. Great, fantastic. Let's see it again. A bit there. I think there you'll see it better. Fantastic. So let's play around. So what's happening here and what we can change. So the first thing is, let's, for example, let's speed up this. Let's put here 2. This is the second action, which is the one that goes like that. So let's have a look. This is the same speed. Well, more or less the same. Let's, for example, I don't know. Let's add another sequence of these. Let's do it to go only right and left at the end. So right, left, and then right again, and then left again. Let's execute it. Perfect. Yeah, so how did I get these positions? Did I do it manually? So did I go here and execute this, which is 1 by 1? Let's execute this. Then ID, for example, number 1, which is the base, and then I don't know, 0.7. And then I keep moving, like number 2. I don't know. Let's not go crazy, because otherwise it could be dangerous. So yeah, I'm not sure which values I have to put. So let's have a look here. So for example, in the node, in the second, we can put 0.6, maybe. There you go. So you can see that this is 1, it's dangerous because I don't know what's going to happen, and 2, it's really, really slow. So how can I do this? Very simple. I stated here in the notebook, but in the part of the appendix, let me just, so how to get complex poses quickly. Of course, it's not the way I've shown you, but the quick way is we go here and we disconnect the controllers, okay? Yeah. Now, for example, whoa, now we want, let's say, I don't know, I want to put this pose, for example, like that. Okay? Yep, more or less like that. Okay. Now I start the controllers again. There you go. Now it stays there. So now it's like making a picture. So now we do a ROS topic. I have my tip here. There you go. Much faster. I go here and I do this. And there you go. So now we have a new pose. So now we go here and let's create a new sequence. I don't know, like dancing or pendulum. So we say pendulum left, bam, here we have it. Now we do the other one, so we repeat the process again. So there you go. Now we do like the middle, we do that, for example. There you go. Again, same thing. Copy, pendulum, and middle. There you go. Be careful when you disconnect because it can hit really hard on the floor. And now let's put it like that, for example. There you go. So now we go here again one last time. We copy and we paste it. Pendulum right. There you go. To get it, oh sorry, now here, for example, let's copy this and we say pendulum and we copy here. I like to always start and finish in the same place, a safe place. Okay, and now we do pen left, pen right, pen middle, sorry, and pen right. There you go. And now we just copy paste. Ah, we really love copy paste, aren't we? It's really nice. I think it's the best invention. Okay, now that we have it, then we add this sequence to the execution and we put it here and we put a time. Let's say, I don't know, like 0.5. Yeah, good enough for me. So now we execute the script. If I get it, there you go. We check that we have the ones that we want. There we go. And now we execute it and see what happens. Perfect. And we did that in what, 5 minutes? Great. So like this, you can register very complex movements and do them really, really fast to pick up objects and this kind of stuff. So I hope to see you building your own robots and doing really, really crazy and funny stuff. So that's it for today. And that's all for today. Thanks a lot. If you liked it, smash that like button twice if you can, 3 if you can, and subscribe because we publish videos every day, live classes, podcasts, tutorials, everything. I think there's nothing we don't do. So in the next video, what we're going to do is, well, it depends on you. Put it in the comments below. What do you want? Do you want that we go deeper into getting the torques and maybe using the API so that we can get those readings and make a safer robot? Or do you want to go straight to Move It Road? Leave it in the comments below. And if you don't, I'll do whatever I want. Thanks a lot, people. And until then, keep building.